Hi everybody, we are in section 10.2, continuing our discussion on parametric curves. Today we're going to be looking at calculus with parametric curves, so performing operations like the derivative, and looking at rates of change, tangent lines, all that kind of stuff when dealing with that parameter t, or sometimes theta, we'll see in this section, instead of just with x and y. Okay, so to start us off, suppose f and g are differentiable functions, and we want to find the tangent line at a point on the parametric curve x equals f of t, y equals g of t, where y is also a differentiable function of x. Then the chain rule gives us the following result for our derivative. So dy dt equals dy dx times dx dt. Okay, so because y is a differentiable function of x, but x is a differentiable function of t, so we have dy dx times dx dt, right? And even though technically these aren't fractions, you could just imagine kind of canceling those dx's with each other, and that would give us the proper result. Okay, that's kind of a shorthand for it. Now, this gives us a solution for dy dt, but if we want to find dy dx, right, the derivative of y with respect to x, as long as dx dt is not 0, that allows us to divide by it, and then we can just isolate dy dx. So then dy dx is dy dt over dx dt. So we get the derivative of y with respect to t, divide by the derivative of x with respect to t. Okay, and of course, bearing in mind that denominator cannot be 0, and that's going to give us our derivative, dy dx. So we can still define derivatives in terms of x and y, even if we're working with a parameter t. Now, if we want to compute the second derivative, all we really need to do here is replace y for dy dx in the formula. So instead of taking the derivative of y, we're taking the derivative of dy dx. Okay. So, and just use that in the formula instead. So we're going to get d dt, so derivative of dy dx over dx dt. That part doesn't change. Okay, so you can look at the similarities between these two, right? This one up here, derivative of y with respect to t. Up here, we have derivative of dy dx with respect to t, and then the denominator is the same in both of them. Okay, so let's go ahead and use these in an example. So a curve C is defined by the parametric equations x equals t squared, y equals t squared minus 3t. So part A, show that C has two tangents at the point 3, 0, and find their equations. Okay, so part A. Alright, so when we're at the point 3, 0, you can look at the x or the y term. I'm going to look at the y. So y equals t squared minus 3t. So the y-coordinate of this is 0. So I'm just going to factor this. So t times t minus 3. And we know that that is equal to 0. Solve this for t. You get t equals 0. And t equals plus or minus root 3. Okay. So that's plus or minus the square root of 3 there. Okay. So these are the different values of t where the y-coordinate is 0. But we also want the x-coordinate to be 3. So we see that if we use t equals 0, that's not going to give us an x-coordinate of 3. That would give us 0, right? 0, 0 as a point. So we're just going to use the plus or minus root 3, because those are the only ones that satisfy both of those equations. So, 3, 0, 3, 0 occurs on C for t equals negative root 3 and t equals positive root 3. Okay. All right. Oh, I apologize. I was supposed to tell you guys. It should be fixed on yours. I just haven't fixed it on here yet. In the setup for the problem, this t squared should be a t cubed. So let me just fix this on here. Get rid of that. There we go. And this is going to be a 3. There we go. So I apologize. On yours, that should be fixed. So you're probably yelling at your screen like, "Hey, why is mine a 3 and yours is a 2?" Oops. Okay, that's starting to make more sense now. Why this answer isn't working? Okay, so this should be a 2, or excuse me, a 3, which means that's a t squared, and that gives us the t equals plus or minus root 3. Yeah. Okay. Sorry about that. So make sure that you got that here. So that's a t cubed minus 3t. So factor out a t, it leaves you t squared minus 3, and then solve. That gives you the plus or minus root 3 there. Okay. All right. That's looking better now. So now let's go ahead. We want to get the tangents. So we need to take the derivative. So we need dy dx. So that's going to be dy dt over dx dt. Okay, so that's going to be 3t squared minus 3, and then derivative of x with respect to t is 2t. Okay, you can pull out common factor of 3. I'm just going to get the 3 halves out to the front here. That leaves you with t squared over t, which is t, minus 1 over t, like that. Okay, so this formula here is going to give us slope of the tangent. Alright, so now we can find the slope of that tangent. So when t equals plus or minus root 3, dy dx equals, so this is 3 halves times plus or minus root 3 minus 1 over plus or minus root 3. So I'll save you the work on that one. Turns out this is just going to give us, again, plus or minus root 3 if you do simplification there. So you can go in and check that and make sure that you're okay with that answer. So our tangent lines, so we're looking for the equations of these tangent lines. So we can use point slope form. So that's going to be y minus 0 equals root 3 times x minus 3, and y equals negative root 3 times x minus 3. So those are going to be the equations of our two tangent lines at the point 3, 0. right? So we get two tangent lines because the curve, it appears, intersects itself, right? It crosses itself at this point. That's why we're getting two different t values and two different tangent lines here. Okay. So let's look at part B. So find the points on C where the tangent is horizontal or vertical. So a horizontal tangent, that's where the derivative equals 0. So part B, so a horizontal tangent, so that occurs when the derivative is 0. So when dy dx equals 0. And also, for dy dx to be equal to 0, if we go back again and remember the formula right here for dy dx, in order for that to be equal to 0, the numerator is going to have to be 0 and the denominator not be 0. Okay, that's the only way that that's going to work. So really we are saying that we want dy dt to be 0 and dx dt to not be 0. Okay, so dy dt equals 0 and dx dt not equal to 0. Okay, so let's go ahead and do that. Okay, so dy dt, so that's going to be 3t squared minus 3, set that equal to 0. Factor out and divide out the 3, that gives you t squared equals 1, which gives us t equals plus or minus 1. So, when is t equal to plus or minus 1? So go back to our original parametric equations up here, plug in plus or minus 1, and you'll see that we get the point 1, negative 2, and the point 1, 2. So those are the points at which we have a horizontal tangent. Okay, so there's our horizontal tangent. And then the vertical tangent occurs when the derivative is undefined. And that's going to occur when dx dt is equal to 0, right? When the denominator equals 0, right? And that's when we get an undefined value. So the vertical tangent so that occurs when dx dt is 0. So dx dt we saw is 2t equals 0. So this occurs when t equals 0. So the only point where t equals 0 is at the point 0, 0. Okay, so just we have our horizontal tangent at 1, negative 2, and 1, 2. We have our vertical tangent at the point 0, 0. All right. And then let's look at part C. Determine where the curve is concave upward or concave downward. Okay, so we're looking concave up, concave down. Hopefully you remember from your Calc 1 that concavity is determined by the second derivative. So we're going to get the second derivative of this function. So part C, so we want d squared y dx squared. Alright, so that's going to be the derivative of dy dt, and dy dt was 3/2 t minus 1 over t over dx dt, which we saw was 2t. So that's going to be 3/2 1 plus 1 over t squared over 2t, okay, which is, let me separate this off here. Okay, so simplify this down. You're going to get 3 times t squared plus 1 over 4t cubed. So to determine concavity, so when it's concave up and when it's concave down, the t squared in the numerator will always be positive. The only thing that's determining positive or negative is that denominator, that t cubed. So it'll be positive when t is greater than 0, and it'll be negative when t is less than 0. So we have the graph is concave up for t greater than 0, concave down for t less than 0. Okay. And then part D asked us to go ahead and graph this curve. So let me get us a sketch here. Okay, so there's x, there's y. 1, 2, 3. 1, 2, 1, 2. Okay. So we know the points 3, 0, the point 1, 2, the point 1, negative 2, and 0, 0 are all on this. Okay. So what the graph is going to look like is going to be something like this. Hopefully I can get a good sketch here. Oops. Let me just, oops. Sketching with the stylus is the hardest part. Let's see here. Maybe this will work a little better. Zoom in. Yeah, that's a little better. Okay, so let's look at these identifying points here. So of course we have 3, 0 showing up over here. We've got 1, 2. We've got 0, 0. We've got 1, negative 2. Okay, so the curve starts from down here. It's heading up that direction. Because remember, so this is where t is negative root 3 and positive root 3. Up here, this is where t equals negative 1. This is t equals 0. This is t equals 1 down here. So we're heading around the curve this way, and then off in that direction. Okay. And then back in part A, those tangent lines that we were looking at to the point 3, 3, that would have been right here and right here. Those would have been our two tangents. Okay. So that's kind of what's going on with the graph. And you can also graph that on Desmos too. Just sketch out those parametric equations. That'll give you a graph that looks something like that. Okay, so that's what we have going on here. You can notice all of the features we've talked about. Okay, the points, the horizontal tangents, right? So we got horizontal tangent up here and down here, vertical tangent right here. We've got the concavity, right? It's concave down for t being up to 0, and then concave up after 0. Okay, so it's got all those features on it for us there. All right, let's move on and look at the next topic here. So this is area. So computing area under a positive curve, y equals f of x from a to b. So normally what we would do is compute the integral from a to b of f of x dx, right? That's area under a curve. If the curve is traced out by parametric equations, okay, f of t and g of t, with t going from alpha to beta, so instead of a and b, then we can calculate the area using substitution. So the particular substitution here, so instead of y dx, we have g of t times f prime of t dt going from alpha to beta. Alright, so everything is going to be put in terms of t. This is kind of an application of the chain rule a little bit, but it's kind of like a u substitution to get this formula. But once we have it, now we can just use it to compute integrals using parametric equations. So let's take a look at this example. So find the area under one arch of the cycloid. So remember the cycloid from last time we talked about, had that interactive graph. So we're looking at, our picture here, something like this, and it goes off in that direction, and it goes off in that direction. But this is one arch of the cycloid, and we're looking for this area under the cycloid. Okay, and we don't know the radius, so that means that it's going to start at 0 at the origin, and it's going to go up 2 pi r units is where it intersects that next one, right? It's only 2 pi if the radius is 1, but it would be 2 pi times r. So we need to get g of t and f prime of t to be able to do this one. So let's get y equals, that's given to us already, r times 1 minus cosine of theta, and then dx equals derivative of theta is 1 minus cosine of theta. So you notice they do give us the same thing. And then d theta. And this is for theta going between 0 and 2 pi. Because one arch of the cycloid is represented by theta going from 0 to 2 pi. If we go past 2 pi, then we're starting another rotation of the circle, basically. Okay, so that's the next arch. Alright, so let's set up our integral. So our area, that was going to be 0 to 2 pi r of y dx. So we get, when we do the conversion, 0 to 2 pi. Y is r times 1 minus cosine of theta times dx gets converted to r times 1 minus cosine of theta as well, d theta. Okay, now r is the radius. R is not a variable in this case. We're just saying that this is true for any value of a radius on this circle. So I'm actually going to pull the r squared out of the integral because r is not the variable here. And if you're wondering whether or not it is, you can look at the differential here. That's d theta, not dr. So that indicates to us that theta here is the variable, not r. So we can pull the r squared out. We're left with 1 minus cosine of r squared d theta. Go ahead and square that out. Integral 0 to 2 pi. That's 1 minus 2 cosine of r plus cosine squared of r d theta. Whoops, did I put r's? I meant thetas. Well, let me just fix those. So 2 cosine of theta plus cosine squared of theta. There we go. Okay. And then this, to integrate, the first two terms are fine. That cosine squared, we need to go ahead and just substitute using one of the double angle identities. So that's integral 0 to 2 pi, 1 minus 2 cosine theta plus 1/2 times 1 plus cosine of 2 theta d theta. Okay. And now this is something we can integrate. So take the antiderivative here, so r squared. Here we have 1 plus 1/2, so that's 3/2. So this is 3/2 theta minus 2 sine theta, and then plus, it's 1/2. So it was 1/2 cosine 2 theta, so the antiderivative is 1/4 sine of 2 theta. You can do a u sub for that if you'd like. Evaluated from 0 to 2 pi. Run that evaluation, you're going to get a lot of zeros, and all you're going to be left with is 3 pi r squared. So it turns out, if you want to find the area under one of the arches of the cycloid, what you need to do is just take 3 pi times the radius squared, whatever the radius is of that circle. All right. So let's go ahead and take a look at the next topic here. So we're just kind of hovering around all these similar topics we've been talking about, but now just putting them in the context of parametrics. So now we're looking at arc length. So if a curve C is described by the parametric equations f of t, g of t between a and alpha and beta, where f prime and g prime are continuous on that interval, and C is traversed exactly once as t increases from alpha to beta, then the length of C is L equals the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. Okay, so this formula, if you want to see the derivation of this formula, it is in your book. So you're more than welcome to go in and take a look at the derivation, but we're not going to take the time to do that in here. So let's look at an example finding arc length with this new parametric formula. So for this example, I do need to fix one thing. So there was another typo here. So these are the only two that I was able to find that I know of. So, so we're trying to find the length of one arch of the cycloid, and it gives the formulas here, but the formula for y should not be theta. It should have an r there instead. So just fix that really quick. Okay, make that a little bigger. There we go. But again, on yours I should have already fixed this already, so you shouldn't have to worry about changing it, just so we're all consistent. Okay, so find the length of one arch of the cycloid. So we need to use this formula. So that's going to be L equals the integral from 0 to 2 pi of dx d theta squared plus dy d theta squared. So you can see we are going to be using theta here, so d theta, as our variable instead of t, but the variable itself doesn't really matter much. So what we have here, so we have, again, theta going from 0 to 2 pi. That's because of the fact that it's only one arch. If it was multiple arches, we would need to go further with theta. But let's see, what else are we going to need? We need dx d theta So take the derivative of that with respect to theta. You're going to get r times 1 minus cosine theta. And then dy d theta, you're going to get r times 0 plus sine theta. So that's just going to be r sine theta right there. All right. So let's go ahead and sub those in. So 0 to 2 pi square root of r squared 1 minus cosine theta squared plus r squared sine squared theta d theta. Okay, and then let's simplify. So integral 0 to 2 pi square root. Factor an r squared out of all of that. And what you have left when you FOIL the 1 minus cosine squared, you're going to get 1 minus 2 cosine theta plus cosine squared theta. We saw that before. And then plus what's left over there in the other term is sine squared theta. Okay. And then d theta. Now, what we have here, cosine squared plus sine squared equals 1. So those are just going to turn into a 1. That's going to add to this one right here. Notice we have an r squared inside the square root. We can pull that out of the square root, and it just becomes r. So I'm just going to pull it all the way out of the integral, because again, theta is our variable here, not r. And then what's left in here is the square root of 2 times 1 minus cosine of theta, d theta. Okay, so that's our simplification. Now to be able to integrate this, so at this point now, this is just a matter of integration. We need to use an identity for this one. So let me do this in a separate color. This is kind of a side note here. So use identity sine squared x equals 1/2 times 1 minus cosine of 2x, with theta being equal to 2x, because that's going to match up this cosine of 2x with the cosine of theta over here. Okay, so that's going to allow us to do a nicer substitution. So we get 1 minus cosine of theta, just playing around with that identity, equals 2 sine squared of theta over 2. Okay, so this is the substitution that we're going to be able to do here. And then let me go ahead and just do our work with the square root right now. So just going to do this as a separate note over here. So note, we're going to need to determine the positivity of the term inside the square root. So since theta is between 0 and 2 pi, that means theta over 2 is between 0 and pi. And if you picture your unit circle where that exists, that is going to be all of the positive y values, or in other words, all of the positive sine values. So sine of theta over 2 will be greater than or equal to 0 for all of these values. That's going to come in real handy, because now when we work with this square root, we're going to have square root of 2 times 1 minus cosine theta, right? That's what's in our integral right now. That's going to be square root of 4 sine squared theta over 2 okay, which is 2 times the absolute value of sine of theta over 2. And then this is again where that positivity comes in, because now we can just dish the absolute value, because we know that sine will always be positive on this current interval. So that gives us 2 sine of theta over 2. Okay, so let me separate all this off here. It's all kind of our side work. Because now we come back to the integral and say this is the same thing as the integral 0 to 2 pi of 2 sine of theta over 2 d theta. Take the antiderivative, so that's 2r times negative 2 cosine of theta over 2, evaluated from 0 to 2 pi, which is 2r times, use the FTC here, you're going to get 2 plus 2, so that's going to be 8r. Right? So we get, again, remember what the question was asking for way back when, was the length of one arch of the cycloid. Okay, so we have our cycloid up here, and we're going from 0 to 2 pi r, saw that in the last one, and the length up here is going to just be 8r, whatever that value of r is. Okay, so we're just learning all kinds of things about the cycloid in this section, but it is a good shape for us to be able to work with. So, all right, so we've got one more topic in this section. Sorry guys, I know it's a long one, but our last one here. So we've talked about area under a curve, under a parametric curve. We've talked about arc length for a parametric curve. And now we're going to work with surface area using a parametric curve. So this one, you can derive the formula similarly to how we do arc length. But we can compute surface area for the parametric equations, where f prime and g prime are continuous, g prime is greater than or equal to 0, and is rotated about the x-axis. So we're getting surface area of a surface of rotation. If C is traversed exactly once, as t increases from alpha to beta, then the area of the resulting surface is given by S equals the integral from alpha to beta of 2 pi y times basically the arc length. So square root dx dt squared plus dy dt squared dt. So this is our formula for surface area using parametric equations. Okay, so for a curve C. Alright, so let's look at an example here. So show that the surface area of a sphere of radius r is 4 pi r squared. So this is a formula that you probably learned way back when in your geometry class, right? The surface area of a sphere, 4 pi r squared. So we're actually going to show this not using geometry, but using calculus. Okay, and that's oftentimes where a lot of those geometric formulas come from, is from calculus. So in order to get a sphere using rotation, using a revolution, so we're going to obtain a sphere by rotating the semicircle So picture this. I have a semicircle like this. So that's just going to be parametrically defined as x equals r cosine of t and y equals r sine of t, with t going from 0 to pi. Okay. So imagine we have this semicircle, right, with t going from 0 to pi, and we take this and then we rotate it about the x-axis. So each point here gets a corresponding point down here, right? So we're going to rotate this. So every point gets rotated. Right, so you can see, whoa, if I can draw a little more accurately, you can see that we will end up getting a sphere here. So a ball of radius r, right? This is just generic. This is not the unit circle, just any circle of radius r. So rotating this sphere about the x-axis. Okay, so let's set up for the formula for surface area. So you can refer to it from the previous page. So this is S equals the integral from it's 0 to pi of 2 pi y, but y in this case is r sine of t times square root dx dt squared plus dy dt squared, so that's going to be negative r sine of t, that's derivative of x squared, plus derivative of y squared is r cosine t, and then square that, dt. So this gives us, let me go ahead and pull the 2 pi out, integral 0 to pi r sine t times square root. That gives us an r squared in both of those terms. I'm going to factor that out, and we're left with sine squared t plus cosine squared t. So that's nice. It's going to work out in our favor. All right, that's a 1. So all we have left is r sine t times the square root of r squared, which is just r, dt. And once again, r is not our variable here because, again, indicating this is the t is our variable. So I can pull out, I have 2 factors of r in here. I can go ahead and factor those out and get them out of the integral entirely. So that's 2 pi r squared times the integral from 0 to pi of sine of t dt. And then integrate. So 2 pi r squared, antiderivative of sine is negative, cosine, from 0 to pi. And then evaluate that. That's going to give you 2 pi r squared times 2. Which is 4 pi r squared. Which is exactly what we wanted to get for the surface area of a sphere of radius r. Okay, so proving a geometric result using calculus. Okay, so we've seen how we can use parametric equations to perform calculus, including derivatives and integrals, and to perform all of these calculations we've looked at, including area, surface area, arc length, all that good stuff. So that's the end of section 10.2. When we come back next time for 10.3,